On a dark night, look up at the sky. How far can you see? Even though all the stars we can observe at night seem very far from us, in fact, they're only a few hundred light years away. On astronomical scales, those distances are almost nothing. That's why it's quite hard to find any trace, with the naked eye, of anything beyond our own galaxy. If I didn't have a telescope that makes more distant things visible, I might think the whole universe was only a few hundred light years across. But there's always one exception in the sky. Thanks to the billions of stars inside them that we know and can define planets, stars, black holes, and so on, the center of a galaxy can be as bright as the light emitted by 2 trillion suns. Despite that brightness, the universe's mind-boggling size and the distance between us and them makes most of these galaxies invisible to us. That's why even today we try to illuminate the mysteries of these giant island universes only with very advanced telescopes. However, among the billions of galaxies in the sky, there's one that doesn't seem very shy about revealing itself to us. If you know where to look in the sky, you can see it using just your eyes without any telescope or binoculars. This galaxy is in the northern sky, in the constellation Andromeda, which has the same name as the galaxy itself. Andromeda's name, like other constellations in the sky, comes from Greek mythology. In the myth, Andromeda is a princess chained to a rock to be sacrificed to a sea monster as a punishment for her mother Cassiopeia's pride. For this reason, in Turkish sources, you may sometimes come across Andromeda being called the Chained Princess. Finding the Chained Princess in the sky is quite easy. For that, you first need to find Cassiopeia, the queen, who in mythology is the chained princess's mother. The Queen constellation resembles a giant W in the northern sky. You can easily distinguish the 5 stars that make up the main outline of this constellation. But to reach Andromeda, we need to focus on the brightest of these stars, that is, the star Shidar. The direction Shidar looks always points toward the constellation Andromeda. After you find the star Merak along this direction, then in the region of the second and finally the third star, the Andromeda Galaxy meets us. However, to the naked eye, the Andromeda Galaxy appears as a faint smudge or a small cloud. Therefore, to be able to see the galaxy, it's essential to be in a dark place far enough away from light pollution. Whether we call it the Chained Princess or Andromeda, the most distinctive feature of this galaxy, unlike other galaxies, is undoubtedly that it can be seen with the naked eye. This situation also makes the question of who discovered Andromeda first meaningless, because thousands of years ago, when there was no such problem as light pollution, anyone who wanted to see it could look up and pick out Andromeda. Once humanity began to understand the Andromeda Galaxy, there was no turning back. This wasn't just about Andromeda, it was the story of humanity discovering its place in the universe and discovering itself. When we look at the efforts to record and define Andromeda for the first time, we go to the year 964 C. In that year, the Persian astronomer Abd al-Rahman al-Sufi cataloged the stars and celestial objects in his book, the Book of Fixed Stars, and in this book, he described Andromeda as a blurry patch or a small cloud. Because it took a long time for equipment like telescopes that would allow us to examine this object in detail to be invented, not much work could be done on Andromeda from al-Sufi's record until the 1600s. For centuries, Andromeda remained a mysterious haze in the sky. In 1612, the German astronomer Simon Marius became the first person to make detailed observations of Andromeda using a telescope. In his observations, Marius noticed that Andromeda's brightness increased toward the center. However, at that time we weren't even aware that our own galaxy was a galaxy. In fact, there wasn't even a definition of galaxy. We thought our galaxy, the Milky Way, was a structure that contained all the stars and everything in the universe. In other words, the entire universe consisted of the Milky Way. This was due not only to astronomy's underdevelopment, but also to the belief that had persisted for centuries that we must occupy a privileged position in this universe. So, as a result of his observations, Marius thought Andromeda was a nebula that should be quite close to us, both because of its brightness increasing toward the center and because of the area it covers in the sky. And Andromeda really does cover a large area in the sky. Like Marius, we can pick out the brightness at Andromeda's center with the naked eye. However, if we could see all of Andromeda bright enough, we would realize it appears even larger than the full moon in the sky. So it was quite natural for Marius to think Andromeda was close to us. In the century after Marius's observations, in 1764, the French astronomer Charles Messier realized there were dozens of different hazy objects in the sky besides Andromeda. Messier was observing comets at the time, and he noticed that because these objects never changed position in the sky, they couldn't be comets. For this reason, although he didn't know that these objects were galaxies, he decided to prepare a list so they wouldn't be confused with comets, and he compiled the famous Messier catalog that is still frequently used today. In this catalog, Andromeda found its place with the number Messier 31. Toward the end of the same century, the German astronomer William Herschel came on the scene and made an interesting observation. He was himself a telescope maker. In 1789, he built a telescope with a mere diameter of 120 centimeters. This telescope was the largest telescope built up to that time. Starting observations with his telescope, Herschel noticed that there was a faint red region in Andromeda's central area. Looking at the red color and brightness there, Herschel mistakenly thought Andromeda was the nebula closest to us. According to Herschel, Andromeda should be only about 18,000 light-years away. In 1845, William Parsons discovered that some nebulae, including Andromeda, had spiral arms, and for the first time he sketched Andromeda's spiral arms in a way consistent with his observations. With Parsons, astronomy gained a new concept, the spiral nebula. That is, according to astronomers, these objects were nebulae with their own spiral structures within our galaxy. The word nebula itself comes from the Latin word meaning mist, so when they said Andromeda, the spiral nebula, they weren't even talking about nebulae in the sense we know today. But the strange thing is that even before Herschel's, Messier's, or Parsons's observations, in 1755 there was a famous name who made a much bigger claim than all these nebula ideas, Immanuel Kant. Kant thought these hazy objects could be other structures located outside our galaxy. Therefore, he used, for the first time, the expression island universes for these objects. In other words, the concept closest to what we today mean by galaxy, or in Turkish, gök-ada, was proposed by Immanuel Kant. This idea of island universes also lit the fuse of a very long, very big debate, because if these objects were other universes, that would require their distances to be much, much greater than what the astronomers of the time, like Herschel, had calculated. So although this wild idea wasn't accepted by many, astronomers split into two. Some supported the view that these objects were other galaxies within the universe, agreeing with Kant, while a large part thought these were regions within our galaxy that preceded the birth of stars. In 1885, a discovery was made that would allow Kant's ideas to be debated observationally. A supernova explosion in the Andromeda galaxy, named SN 1885A, became even brighter than Andromeda itself. But at that time the distinction between supernovae and novae wasn't known. According to Harlow Shapley, since a nova couldn't be as bright as an entire galaxy, Andromeda couldn't be a galaxy-sized object. This observation allowed Kant's island universes idea to be discussed, but another astronomer named Heber Curtis approached this observation from a different angle. Up to that time, other novae had been seen in completely different regions of the sky. However, along with SN 1885A in the Andromeda galaxy, many other novae were also observed there. This situation, observing many novae in a small area of the sky, required that Andromeda be much farther away than our galaxy, because if Andromeda were a nearby nebula to us, that would mean a great number of nova explosions were happening in a very small area of the sky. The debate between Heber Curtis and Harlow Shapley went down in history as the Great Debate and became one of the most important milestones in the history of astronomy. If Heber Curtis was right, the universe was much, much larger than we had thought up to that time. That would also show that we weren't in a privileged position in the universe, as we imagined. If Curtis was right, we had to accept that we are just a tiny speck of dust in the universe. There wasn't a clear winner of the debate because we couldn't measure the Andromeda galaxy's distance. The distances of nearby stars could be measured, but as distance increased, making measurements by the parallax method became progressively more difficult. We needed a more modern and different method to be able to measure the distances of galaxies. A few years after the beginning of this great debate without a winner, in 1923 Edwin Hubble was searching for a Cepheid star in the Andromeda Galaxy with the 2.5-meter Hooker telescope at Mount Wilson Observatory. Of course, there was an important purpose to Hubble's search for a special type of star in Andromeda. Cepheid variable stars are stars whose brightness changes over time intervals of 1 to 120 days. Since these stars have reached the last stages of their lifetimes, they swell and then contract again. In other words, these stars are pulsating stars. Because this happens in a specific pattern, when viewed from Earth, we see regular, periodic changes in their brightness. Just like the steady flicker of a candle, the brightness of Cepheid variables rises and falls at regular intervals. That candle-like brightness change is very important. Imagine a candle located at some random distance from us. We know how bright this candle appears from where we are. We call that its apparent brightness. However, it's not possible to determine the candle's distance using only apparent brightness. For that, we need to know how bright the candle actually is independent of distance. In other words, its absolute light output. If you can determine the candle's absolute light output, since you also know its apparent brightness, with those two pieces of information you can calculate how far away the candle is. Therefore, if we want to measure a star's distance, we must know its true brightness. This is where Cepheid variables come in, because in the years before the Great Debate, Henrietta Leavitt had discovered a relationship between the pulsation periods of Cepheid variables and their absolute luminosities. Known as Leavitt's law, this period luminosity relation allows us to determine a star's true luminosity. That is why Hubble reasoned that if he could find a Cepheid variable, i.e., a standard candle, in the Andromeda Galaxy, he could calculate the galaxy's distance, bring the long-standing Great Debate to a close, and at the same time solve the mystery of this hazy cloud that had been visible in the sky for centuries. On a photographic plate coded H335H, Hubble made a 45-minute exposure. After examining the photograph, he marked 3 stars here with the letter N, which stands for nova, because these objects had not been present on earlier plates and had newly appeared. But Hubble marked one of them in big capital letters with a red pencil as VAR, because unlike the others, he realized from its brightness variations that the star named M31, V1 was a Cepheid variable, and therefore the key to a great discovery. If he could determine the period and mean apparent brightness of the Cepheid he found here, he could calculate the distance to the Andromeda Galaxy and bring the Great Debate to an end, while also solving the mystery of that hazy cloud in the sky. Continuing his observations, by the end of 1924, Hubble had found 36 different variable stars in Andromeda, 12 of which were Cepheid variables. Using his observations and all this information, Hubble determined in 1929 that the Andromeda Galaxy is about 1 million light-years away from us. Of course, today, with far more advanced telescopes and more precise calculations, we know that the Andromeda Galaxy is 2.5 million light-years away. So Hubble in fact found Andromeda's distance to be closer than it really is. But even 1 million light-years was enough to say Andromeda is a completely separate galaxy. With Andromeda truly being another galaxy, we suddenly began to grasp that the universe is a much bigger place. With this discovery, the winner of the Great Debate was Heber Curtis. At the same time, we understand that Immanuel Kant, who had proposed the idea of island universes, was basically right from the beginning. It was as if we were looking at another universe in the sky. The Andromeda Galaxy holds the distinction of being one of the most studied and most photographed celestial objects to date. Since the invention of the telescope, both amateur and professional ground and space-based telescopes have photographed this galaxy hundreds of thousands of times. In other words, we now have more information about Andromeda than ever before. In fact, the basis of all the information obtained about Andromeda so far is how well we can photograph it. When it comes to photographing celestial objects, we never talk about single, instantaneous frames. Celestial objects appear much fainter in the sky than our eyes can see. Even with telescopes, a single snapshot of a galaxy is quite low in detail and faint. Therefore, to reveal all the details of an object in the sky, you need to collect the object's light for as long as possible. We call this exposure. So the longer you expose a faint object, the more light you collect and the more chance you have to reveal the mysteries of that object that normally appears faint to us. Because of the area it covers in the sky and its brightness, Andromeda is one of the most suitable targets for long exposure. This Andromeda photograph, which looks like it was obtained by a space telescope, was actually taken specially for this video by Ajit Kayali. Using his telescope in Texas, Ajit Kayali did a total of 11 hours and 45 minutes of exposure to obtain this image. In the resulting view, we can see Andromeda with its spiral arms and the brightness at the galaxy's core. This curved structure is likely a result of the gravitational interactions Andromeda has had with the dwarf galaxies around it. In the photo, structures that are too bright to be stars and resemble nebulae near Andromeda should catch our attention. These are Andromeda's largest satellite galaxies, Messier 110 and Messier 32. Also, if we look carefully, we can see a great many galaxies in the background of the photo. However, these are galaxies much farther away than Andromeda. All these details, along with proper astrophotography techniques today, provide a terrific example of how exposure can reveal detail. Although the gas and dust responsible for Andromeda's hazy appearance in the sky look pleasing to the eye, they can also sometimes prevent us from obtaining accurate data regarding the brightness of the galaxy's stars. If we want to get to know the Andromeda galaxy better, we should examine it not only in visible light, but also at different wavelengths of light such as infrared. That is where space telescopes actually come into play. For example, this is a composite infrared photo of the Andromeda galaxy taken by the Spitzer Space Telescope. We call it composite because, since the Andromeda galaxy is so large, Spitzer made 3,000 separate exposures to obtain these images. The main purpose of this study was to measure Andromeda's total infrared brightness, because the amount of infrared light coming from stars in a galaxy is directly related to the mass of those stars. Therefore, by taking these pictures, Spitzer also revealed the Andromeda galaxy's stellar mass. According to this, the stars in the Andromeda galaxy have a mass equal to 110 billion times the mass of the Sun. This value also gives us the chance to make accurate estimates about the number of stars in the galaxy. According to these values, the Andromeda galaxy should host roughly 1 trillion stars. For comparison, for example, the number of stars in our galaxy, the Milky Way, is roughly about 200 billion. The width of Andromeda from one end to the other is about 260,000 light-years. This means that a beam of light starting at one end of Andromeda would have to travel for 260,000 years to reach the other end. Again, for comparison, the size of our galaxy is about 100,000 light-years. So we're talking about a galaxy that's much larger and much richer than the Milky Way. Despite all these differences, the Andromeda galaxy, just like the Milky Way, is a barred spiral-type galaxy. That is, the stars at Andromeda's center form a bar-like structure, and the spiral arms spread out from there. Because Andromeda's appearance is quite tilted from our point of view, we cannot easily distinguish this central bar structure in photographs. In other words, we cannot look straight down on Andromeda. However, when the motions of the gas and stars here are examined, it turns out that the galaxy's center must have a barred structure. This bright center of the galaxy is also an indication of a supermassive black hole. The black hole here has a mass about 140 million times that of the Sun. Despite this mass, this black hole is, surprisingly, one of the least active supermassive black holes among galactic centers. We can tell this from the relatively low amount of radiation emitted by this black hole, because the gas and dust accumulating in the accretion disk around a supermassive black hole heats up before falling in, and this causes significant amounts of radiation to be emitted by the black hole. Therefore, how active the supermassive black holes at galactic centers are depends on how the matter falling into the black hole behaves, in other words, on how quickly the black hole consumes the matter around it. The low emission at Andromeda's center shows us that this black hole consumes the matter around it at a small but steady pace. In this photo taken by the Spitzer Space Telescope focusing on Andromeda's center, we can see how the dust around the black hole moves. In astronomy, thanks to filters that allow different wavelengths of light to pass through, we can see gases, dust, and stars separately in photographs. For example, when we observe the Andromeda Galaxy in a band that reveals only dust, we can see Andromeda's skeleton. Therefore, this photo reveals not only how dust moves near the supermassive black hole in Andromeda, but also how it moves throughout the entire galaxy. We can see that a spiral arm is dominant in the Andromeda Galaxy, and that it also splits into two parts on the right side of the photo. This may be evidence of the gravitational interactions Andromeda has undergone. Of course, a large galaxy like Andromeda cannot be alone in its region. Andromeda's largest companion, the galaxy Messier 110, is bright enough to be seen even with a small telescope. Messier 110 also appears in the Andromeda photo taken by Ajit Kayali. Although from a distance, it looks like a small copy of Andromeda, when we zoom in on this galaxy, we see that Andromeda's spiral arms are not there. That's because Messier 110 isn't spiral, it's an elliptical dwarf galaxy. Since elliptical galaxies don't have spiral arms and star-forming regions, these types of galaxies are often called dead galaxies. Also, the stars in elliptical galaxies are older than those in other types of galaxies. This small elliptical galaxy hosts about 10 billion stars and also 8 globular star clusters detected so far. When we look at photos of the Andromeda Galaxy, another prominent brightness besides Messier 110 catches our eye. This is Messier 32, another large and bright satellite galaxy of Andromeda. This satellite galaxy is also a dwarf elliptical galaxy, and as with other elliptical galaxies, it consists mostly of red and old stars. Since it contains almost no gas and dust, it's not possible to talk about star formation in this galaxy like in Andromeda's spiral arms. However, this satellite galaxy also hosts a supermassive black hole with a mass equal to 5 million suns. We know this from the radio and X-rays emitted from the galaxy's center and from the gas concentrated there. Most of the Andromeda Galaxy's satellite galaxies are within a region of about 1 million light-years, but the satellite galaxies Messier 32 and Messier 110 are quite close to Andromeda. For example, if the Andromeda Galaxy is 2.537 million light-years away from us, the galaxy Messier 110 is 2.674 million light-years from us. That is, there is only a 100,000 light-year distance between them. Even from 2.5 million light-years away, the Andromeda Galaxy covers a larger area in our sky than the full moon. So if we imagine being on a planet somewhere in the galaxy Messier 110, what would the sky look like? Even if not exactly this view, thanks to today's space telescopes, we can obtain images that take us on a journey inside Andromeda without having to go to its satellites. This is the largest and sharpest photo of the Andromeda Galaxy taken to date by the Hubble Space Telescope. The entire photo consists of 1.5 billion pixels. In other words, if we wanted to see this photo at full quality, we would have to place more than 600 HD television screens side by side. In this Hubble photo, we are looking at hundreds of millions of stars within a 40,000 light-year region of the galaxy. Along with these stars, when we look at some parts of the photo, we can also see star clusters. Up to now, about 460 globular star clusters have been discovered in the Andromeda Galaxy. The most notable of these in terms of mass is the male 2-globular star cluster. This cluster contains a few million stars all by itself and is about twice as bright as Omega Centauri, the brightest globular cluster we know in our own galaxy, the Milky Way. These values are much higher than what a typical star cluster should have. This suggests that the male 2 or G1 globular star cluster is the remaining core of a dwarf galaxy consumed by Andromeda in the past. Unlike the Milky Way, the globular clusters in the Andromeda Galaxy have a much wider age range. While some globular clusters are as old as the galaxy itself, we also come across clusters in this galaxy that are only a few million years old. As we wander through the Andromeda Galaxy, encountering star clusters, star-forming regions, and even black holes at every turn, we really start to feel, as Immanuel Kant once said, as if we're looking at a completely different island universe. This inevitably brings to mind the question, are there also other planets orbiting stars there? On paper, the answer is yes. According to the dynamics of star and planet formation, almost every star in any active galaxy should have at least one planet. Of course, to be able to talk about the possibility of life on these planets, we need to have information about many parameters, such as what kind of star the planet orbits and in what orbital period. So even though in theory we know that exoplanets must exist in the Andromeda galaxy, observing them directly, at a star in a tiny corner of another galaxy millions of light years away from us, is a real challenge for today's astronomy. None of our telescopes, including the James Webb Space Telescope, have resolution power that high. However, in the universe, large mass objects like galaxies or star clusters can act as natural telescopes by bending light. That is, for example, on its journey to Earth, the light of a planet can be bent by a high-mass object. We call this the gravitational lensing effect. This normally makes the light of some objects that are at distances beyond the resolving power of our telescopes visible to us. In 2009, astronomers detected clues to the existence of an exoplanet in the Andromeda galaxy using the gravitational lensing method. The existence of this exoplanet, named PA 99N2, is not confirmed, but still, PA 99 is the first exoplanet whose traces have been detected in another galaxy, an extragalactic exoplanet. However, planets in the Andromeda galaxy don't always have to be together with their stars. As in our own galaxy, where we've detected dozens, there should also be a large number of rogue planets in the Andromeda galaxy, flung out of star systems and left to wander alone in the darkness of space. Talking about the possibility of life on any of all these exoplanets would be speculation, since we have almost no data on this. But when we consider Andromeda's size, its variety of star types, and the richness it contains in terms of star-forming regions, it's certainly true that the possibilities sound exciting. Andromeda, which resembles a completely different universe in the sky, may seem like a place impossible to reach at a distance of 2.5 million light years. However, everything in the universe is in uninterrupted motion. Of course, Andromeda is too. According to the Doppler effect, as an object moves away from us, the frequency of the light coming from it decreases, which causes its light to be redshifted. Conversely, because the frequency of the light coming from an approaching object increases, its light is blue shifted. In the universe, the redshift shown by galaxies indicates that galaxies are moving away from each other. But among all these galaxies that show redshift, Andromeda shows the opposite effect, blue shift. That is, unlike the other faraway galaxies, Andromeda isn't moving away from us, it's approaching us. However, until 2021, we didn't know exactly when and at what rate Andromeda was approaching us. With the help of the Hubble Space Telescope, between 2002 and 2010, the span of 8 years, the motions of stars in the Andromeda galaxy were examined relative to the background galaxies behind Andromeda. When the average motion of thousands of stars was taken, it was discovered that Andromeda is moving across the sky at a speed of less than 0.1 milliarcseconds per year. That is, Andromeda is indeed approaching our galaxy at a speed of about 110 kilometers per second. In fact, this is not a surprising or extraordinary discovery, because mergers of galaxies within galaxy groups are relatively common phenomena in the universe. The very thing that allowed Andromeda's morphology to take the shape it has today is mergers it underwent with dwarf galaxies billions of years ago. We can see the traces of these mergers in Andromeda's spiral arms. Andromeda is indeed approaching us. However, we also know that this approach will take place over time spans much longer than a human lifetime. If we think from Earth's point of view, in 2 billion years at this speed, Andromeda's disk will have grown noticeably in the sky. In 4 billion years, when we look up at the sky, we would witness Andromeda covering our entire field of view. At that time we could see, shining brightly in the sky, the new star-forming regions that emerged as a result of the merger of the two galaxies. For a few 100 million more years, this merger would continue, causing the arms of both galaxies to look asymmetric due to gravitational effects. In the 5 billionth year, finally, the cores of the Andromeda and Milky Way galaxies would also be seen as bright aggregates. When the total period of 7 to 7.5 billion years is completed, the cores of the galaxies will have merged and formed a completely new galaxy. However, because the spiral arms will have dispersed and the rich star-forming regions will have been exhausted, this newly formed galaxy will be an elliptical galaxy. Although we know this scenario will play out 7 billion from now, we will never observe it here as we are imagining, because by then our sun will have long since completed its lifetime and swept away the entire solar system.